Hello and welcome to episode 4 of me working on this thing with Lexing in C++ code for 4coder with the structure model. Doing optimization stuff still. Last time I told you what we were going to work on actually. I said we're going to work on this action list optimization thing, and that's exactly what we're going to do. So let's figure out how to do that. So this might require some drawing at some point, but essentially all of our action lists happen right here. And what we want to do is we want to visit every action list, and for each action list we want to see if it has a consume in it. If it has a consume in it, then it's fine. We don't change it. If it doesn't have a consume in it, then what we're going to do is this and this are going to, what we're going to do is look at the next destination state and try to say, okay, if I applied the same condition, this condition here, to this destination state, what handler would catch it? Now the problem is, this condition here might have the ability to be caught by more than one transition handler over there. So then what we actually have to be able to do is we have to learn how to split transitions into sub cases and that are non-overlapping parts of the original case, and we might need to do that an arbitrarily many number of times and recursively fill out all of the details, right? So it's pretty non-standard, non-trivial stuff we have to do. So I kind of want to think that through a little bit. Essentially what I need I need a language for saying, hey, here's a case and here's a case. And here's a case that, if this is the case that I know I'm in one of these things, right? I'm saying here's the case that we're saying, put in our head, we're in a scenario where this case has come true. We are trying to execute this case handler. Or rather, we are in the situation where this case handler needs to do, where this case handler has been fulfilled. This condition has been fulfilled. That's the way I should put it. We're in the situation where this condition has been fulfilled. The conditions of this case here have been fulfilled. And we are attempting to do all of the actions that that condition should lead to. Therefore, I need to be able to say, does any part of this condition get fulfilled by this other condition? And if so, what is the part of your first condition that gets fulfilled by that one, right? So let's see if I can answer that. Basically, that's kind of like the ecliptor, and it might actually be the same thing as the ecliptor. So let's think that through. Maybe we can just reuse the ecliptor for this purpose. If we can, then great. We're already making huge steps. So what the ecliptor does, the ecliptor says, does any part of what this case handler we're checking, and this one is trying to eclipse this one, right? Or this one has already been, this case handler has already been applied, so all of its cases override this one. Does this have anything that it can do that is not handled here? That's what this answers. So that's not exactly what we want. What we want is something that's more like, if this is my primary, is there anything that this handles that this also handles? And what is it? So this was kind of like a subtraction. If you think of this as the set, alright, let's think about it that way. That's what we need to do. Transition case really is just a set that describes a subset of the possible configurations for, let's pop all the way back to this thing, E and S. So Q is our state. It's not a part of this case stuff. Cases are one of these, right? Well, remember, one or more of, so whenever we're live, during execution, we have one value from the set E and one value from the set S. And so what a case is it's just a set of things that, such that if one of the things in that set matches the actual runtime situation, that case is fulfilled, right? To put it another way, we have the pair of an input value and a bit field, the value of the flag field, basically, right? And given that, that's the actual situation. We're trying to find out which case that it conforms to, and each case is a set of one or more things that look like that type, an input and potential values for the flag fields. Now, it can be more than one, right? The set can contain, it can say I have everything from A to Z as a possible match and any flag field, right? So it's the set of all flag fields combos with letters from A to Z. So they're sets, right? But they're sets with lots of combinations being represented as just a couple of things. And the way we actually, like, we can't have just any set at all in that whole, like, in that conceptual space of all those types of sets. We can't have them all. We can only have the kinds of sets that are represented by a character array, an end of file, or a fallback. And these only conceptually represent portions of the set space. Like, this only represents one particular character always. A case handler that has this can't also be a case handler that can catch the letter A. A fallback can catch everything. We're ignoring this one, like I've been saying. If we see this one, we'll have to figure out what to do about it now, but we're still not going to try to, like, figure out how it interacts with the system. The only way the interaction we're going to have is that we say, if we were trying to figure out how to jump into this state, and it has one of those, what do we even do? It will be different. It won't be like this matching primary to primary thing. But this, and this, right? And there's a set of characters and so on. Then when it comes down to which flag, what flag field values are possible, either all of them are possible, or all of them are possible except that one of the flags is set to a particular value. So I can say, like, the third flag must be 1, the third flag must be 0, but I can't say the third flag must be 1 and the fourth flag must be 1, because that's two different flags being pinned down. So I don't have a whole lot of options on how these sets can carve up the set space. So all I really need to do is, if this is a subtraction, I call this eclipse, but really, I mean, I called it eclipse because that's how I picture set subtraction anyway, now that I think about it. But what I need now is an intersect. Alright, what is the intersection between A and B? What are the cases that occur when both of them are, like, true, right? Now, this I'm going to do like this again. We're just going to say, look, what's the case kind of A? If the case kind is this, okay, so if I have a character array and B has a character array, then there's actually a kind of situation where we don't know the answer to this question. Now that I think about it for a minute, there's totally a situation where we can't do this. Because how are we ever going to intersect two sets that refer to different flags? Right? If two different cases, if case A says, I apply when this flag is 1, when flag number 1 is 1, and B says I apply when flag number 2 is 1. Well, they both apply when both flags are 1, but I don't have any way of encoding that in the current transition case system. Now, I could expand this to allow me to pin down any number of flags. That might be the way to go, because then I think the rest of these, I can intersect character arrays with each other. I can intersect this with itself to get an EOF, or with this to get none. I can intersect this with itself to get none if none of them overlap. I can intersect anything with a fallback as long as I know all the things that came before that fallback and eclipse them out, essentially. You know what I mean? So, like, the intersection of a fallback and well, any case that is a fallback is essentially whatever's left over after you eclipsed out everything else. Anyway. But I don't have any way of representing that. In fact, I'm not sure that this eclipsing thing even works right. Oh, that's right. So this is not exact. This does, like, if the fallback here, if my primary is a fallback, and then the ecliptor is also a fallback, then they eclipse each other because they're in the same space, right? Right. Yes. Whereas here, if I have two different fallbacks, which things can operate as a fallback, like which characters can match that fallback, is determined by the stuff that came before it, right? Everything that wasn't handled by a fallback is handled first and gets eclipted out. But my eclipter doesn't think that way. My eclipter thinks of these as saying, look, I don't actually have to think about the specifics of what this can match. I just need to be able to say that if I'm comparing it to another fallback, then that fallback trumps me. Right. So this is not that simple at all. I don't think using transition case alone will get us there, now that I look at it that way. We might need to make a thing that's a little bit more sophisticated, like a case set or something like that, or a condition set or something that lets us fully represent the set of possibilities flowing through the system, so that we can do the intersections properly and build these things out. But that's going to mean that our transition conditions themselves can't get rewritten, which is what we intended to do from the beginning, which is to split a transition into two transitions with non-overlapping conditions. Not sure that that's even possible, the way cases work. So I probably need to relook at cases and figure out how I can turn these kinds of cases into cases that are fully descriptive of the set space. If I want to continue with this particular theory of how this whole thing needs to fit together. So let's go back down here to where I was saying what I need to do. What I'm trying to do is do this action list optimization thing. And if we take out flags for a minute, then the rest of this gets a little bit easier, but fallback is still a problem too. So if all I had were character array cases, right? If all I ever had for a case was whether or not it matches a particular input, right? One character at a time, this would get really easy, because then all I have to do is say, look, there are no flags, there's no EOF or fallback, I just have, and there's not even character arrays, it's just a single character. So the case that I'm on has a particular character. The state that it transitions to must have a transition that handles that character as well. That's the one I want, right? So the problem I'm having is that each of my transition cases actually handles a set of characters, and what I want to do, or a set of input possibilities, and what I want to do is I want to say for each individual input possibility, where does it land, without having to iterate the many, many possible input combos that represents, but by rather having an abstract concept that says, I am the set of possibilities, and you can refine me by taking characters out, by pinning down more flags, right, and so on. So I think we actually need to do that. So this is the high-level concept of what a transition case condition looks like, but we need to be able to translate that into a precise set of matchings. Again, ignoring this thing. And then what we need to do is we need to rewrite all of our transitions to use that precise transition case set instead of just a generic high-level transition case description thing. So when we do that rewrite, we want to mark all of the transitions as no longer having one of these and having one of the new things, right? How are we going to do that? Well, I could just say let's rewrite a transition case to actually be the fully descriptive, fully configurable set space description thing. And then when I generate them initially, I will just have to generate them from these rules. But the problem is fallback is kind of a semantic meaning that I can't resolve until after I've done some of these other things. Like the thing that simplifies transitions, the thing that iterates them, it just gets a little bit weird trying to make fallback work in a different universe. I guess we could do it though. I guess there's no reason I couldn't do it. It's just, okay, so here are the only things that are going to be tricky. The Dylan match thing is going to be like a sore thumb all the way through this. It corresponds to the worst part of Lexing C++. When you want to do it cleanly, there's one little thing that you can't do the right way. It doesn't work like anything else does. And you need this Dylan match thing. And that's just going to be a problem. But ignoring that part of it for now, because we're going to figure out how to fit that into the system at a later time anyway, and we're going to kind of work around it during this particular optimization. What we're going to do is we're going to say, these are not really there. These are wrong. So a transition case kind is either going to be a Delim match, in which case that's the whole thing. Delim matches I don't even think are allowed to be peaks in the first place. Yeah, you can see right here, match delimiter doesn't have a peaked version. It has a flagged version, but no peaked version. And if we were trying to look at a state and say, what if I am peeking into this state and trying to see if I can complete it, you wouldn't be able to, because these, even if you did get that far, it turns out that you have to let this delimiter matcher run itself. You can't skip over it ever, because it basically hides a consume operator inside itself. So yeah, we basically have either you're a Delim match case or you're a describing, what would I call it, like a set input set, or input space set, or input space, or input state set, or something like that, or input flag set. Condition set. There we go. That's going to be like that. That's going to go away in favor of okay, so that's a pretty complicated rewrite. Let's see what everything that breaks. That goes there. So when I'm creating one of these cases, I don't want to change this interface. I want this interface to keep working. So everything that has to do with actions and destination state stays the same. The condition part is encoded by this, this, and this, and this, and I don't want any of those to change. And now that I highlight that that's the truth, I also want this to be laid out in such a way that it reflects the grouping in a way that makes sense. Okay. So I want this section here to remain the same, but the stuff it's filling can change accordingly, right? So we kind of want a situation where it's like transition case kind actually maybe is different from condition kind or something like that. This is a condition kind, because this here still needs to be like one-to-one match to like character array, EOF, and fallback, because those are the things that the calling code is going to try to pass in. Now, that means that this kind here can't go straight in like that. What actually has to happen is when we're filling in this condition, we're going to switch on the kind we were passed, and in this case, for instance, all we have to do is pass down the condition, pass down the transition condition kind delim match. On each of these cases, we're gonna, besides that one, we're gonna do a condition set. So there's, shit, I did it again. There's character array, end of file, and fallback. Now, the next thing is, when I get one of these, I need to initialize the inputs correctly, and then this flag thing is also going to be, just turned out completely wrong. But they're all kind of going to have a lot of similarities in that respect, so what I kind of want to do is I want to say that the flag part gets handled separately from the character case part, and the flag part looks like this. It goes, if after initialization, my condition kind is a condition set, then do this code. Now this code's actually wrong too, because this needs to be a set, like a list of pinned down flags that can be like more than one pinned down flag, right? So that up to all of the flags can be pinned down, or they can all not be pinned down, or any in between portion, right? I don't think we need states that are like we don't need to be able to represent sets that have like, oh, for this input this state flags, and for this input this state flags. We can always divide it up along the lines of states have, or these state sets that we're creating have every permutation of their possible inputs with their possible, or every combination of their possible inputs with their possible flag states as a part of their set space, basically, right? That's the set that they form. I never need to poke out an individual thing without poking out an entire, like, either all of the input of that type or all of the states of a particular pattern. Or all this, like the flag patterns, I guess, all of a particular flag pattern at a time. So I think that should be fully expressive enough once we get there. Now what we have to do is, this is not a string copy anymore. What happens now is quite a bit different. For each of these, we do a different thing. So in this case, for instance, all we do is we go transition condition inputs equals, we push an array onto our arena with one U16 on it. That will automatically pad out for us, so we don't have to worry about that. And the value of that one input is 256. That represents end of file, right? And then I guess I should like pull that out up here. It's an internal. Okay. So, and then that's input count 1. So that one was the easy one. If I have a character array, then what I need to do is, for every character, we're going to need a specific value in the input. So this is going to become characters.size, and then we do a loop over our characters, and as we go, we store in there just whatever was here, right? Just copying it over to a different type, because these are 16-bit, these were 8-bit. And then the count needs to be this. Right? Okay, so those two are not that hard. Fallback is going to be a lot harder, and we actually can't do fallback correctly without doing flags correctly first. So let's switch gears and figure out how to make these flags work in the new system. We need condition flag. We're going to need the ability to chain these together, and each one has to have a flag and a value. And then we need a transition condition flag, first flag, last flag, flag count, right? So those initially are going to be 0, but if we have a flag to emit immediately, then we're going to grab one of these out of our memory, one condition flag. The cond flag now gets the flag pointer, and it gets the flag value, and then this thing needs to get pushed onto the singly linked queue at transition first flag, transition last flag, Here's the condition flag, and then the transitions flag count needs to go up by 1. Alright, so there's our flags. That's how we'll encode this now, is if we have a flag, we'll push it onto this list that we want to pin it down. And we might want to pull out a helper that says, don't ever let us pin down a flag twice in opposite ways. Just assert if you try to do that. That shouldn't be allowed. If you are going to do that, like maybe a thing that says, like, hey, return false if this would insert like a redundant, or if this would insert a contradictory flag, return so. And then finally we want to be able to say what is the so yeah, we want to be able to say do this insert do that. Sorry, I'm getting sloppy here. Do this insert. Don't let us insert on a contradictory flag, and avoid inserting redundant flag pins, even if it's not going to cause problems that we tried. We'd at least want to avoid putting the flag in there twice, because that's just going to confuse some of the algorithms. So we're probably going to need to write a couple helpers for that, but I just wanted to get the basic structure in place to guide me through this part, which is going to be the really challenging part. So when we insert a fallback case, what we really need to do is look at all the cases that are already in the state and figure out which inputs are not yet marked off, right? And the point is the flags are correct. We're not going to alter what set of flags go in. So what we want to do is we want to say, hey, if these are if the flags are pinned in this particular way, we can say anyone who doesn't pin any flags will still match us. Anyone who pins flags in contradictory ways, we can ignore them. And anyone who pins the same flags or more flags, like anyone who's, basically if we look at some other case and it has its own flag list, we want to look at our two flag lists and say, hey, I pin these things down, you pin those things down. Do we contradict each other? Because if we do, we never overlap. And so the things you handle, I will always be responsible for picking up the slack, right? Even if you handle all of the input, if you're a fallback and you pin this bit to a 1 and I pin it to a 0, you don't eclipse me in any way, basically. So essentially what we're doing here is we're running an eclipter, just we're running it at the time when we generate these sets to begin with, and we're running it starting from a transition case that has all possible inputs, but these particular pinned down flags. And then we are going to, right, I get it, I get what we got to do. So, how do I want to do that? I want to, and this doesn't fix the problem that suppose someone else pins, so if my pinned flags agree with your pinned flags. Okay, so there's actually 3 scenarios. There's you contradict me, so that anytime what I pin and you pin are opposite, you contradict me, therefore you will, anytime you don't handle something, it will fall through and I will want to handle it. Right? Like, supposing I have that input character too. So you don't affect me at all. But suppose there's someone who pins a flag that I do not pin. Suppose they say they want to handle this situation when flag 1 is true, and I say I want to handle this situation when flag 2 is true. We both are trying to handle the same situation. What happens? Well, sometimes they would eclipse me, but other times they wouldn't. Basically, anytime the thing that they're pinning down is a 1, even if my thing is also a 1, theirs comes first, so they go. But if their thing is a 0, then I have a chance if the flag I'm looking at happens to be a 1, right? So I can't be eclipsed by that, but I should mark myself as only handling situations where that flag is a 0, but only for those cases where, oh dang, only for those cases where our inputs overlapped. Whew. Non-trivial. Okay. Yeah, so that actually is a situation where you can't represent the set as just a set of flag pins and a set of inputs, because suppose you and I have intersecting but non-equivalent and non-like hierarchical sets. We have intersecting sets, but we also have non-zero sort of the subtract. How should I don't know what the most succinct way to say is that we both have members that the other does not have, but we form a Venn diagram, me and you, okay? And you're a case handler and I'm a case handler, okay? Our input sets are form a Venn diagram. They have non-zero intersection, a non-empty intersection, but we also both have inputs that we handle that you do not handle, that the other one of us does not handle, right? Furthermore, we both pin a flag, but we pin different flags. You're a case handler and I'm a case handler, and you go first. All the characters you can handle when flag 2 is set to 1 need to be eclipted from my set. However, that means that I am a case handler who handles the same set of characters I used to handle, but for some of those characters I handle them only whenever bit 1 is set to, and that's it. But for another portion, the portion that I intersect with you on, I can now deduce that I only handle them when my bit is set to 1 and when your bit is set to 0, right? And so those are two different subsets of my set that I want to specify. So there's a couple ways I could do that, and I might not need to, so I need to think that all through. So for one thing, keeping in mind the goal here, right now I'm just trying to encode enough information to get the same behavior that I used to get. And if I don't bother to represent the fact that I could deduce more information about my bits from the fact that I'm eclipted by your bits, I don't have to, right? You don't contradict me, so we have non-overlapping bit patterns that we pin down, right? My bit and your bit don't even interact with each other. So I can just say, look, whenever my bit is set, I handle these characters. And, you know, like under my breath, it turns out that at one point I noticed that you were going to handle some of those characters before I was going to get a chance to handle them. But you weren't always going to do that. And the times when I was going to apply were independent of the times when you were going to apply, according to our bit flags, or according to our flag checks. So I just didn't even bother to write that down. I just said if it gets past you, then I will work on it, and I don't take the time to note that it could potentially get past you. So the situation that creates is that this would work correctly at generation time, but what would happen when I went to do this optimization that I'm trying to optimize for right now, this thing? Well, what this thing is all about is saying I'm a state, or I'm a transition from a state to another state, but I don't consume a character along the way of that transition. So I want to look at the state I would transition to and grab its actions and pull it into me, and I want to grab its destination and pull it into me, but it's not that simple because my case here is actually, or my transition here is defined as a set of possible conditions that I can satisfy. And so they don't necessarily all behave the same way in the destination state. And I need to be able to, before I can do anything else, split my transition into all of the, into the set of sets, into a set of transitions so that they have non-overlapping, perfectly non-overlapping conditions. Now that shouldn't be too hard, as all that's going to happen is we're going to be splitting the inputs and adding in flag pins, right? So it might be, for instance, that I look at a character A, B, C, or D, and it turns out that if I see a character A, B, C, or D, I don't do any flag checks, and I transition without consuming the character to a particular state. That state then says, look, if I see an A or a B, I consume it, and I go to state, X. If I see a D or an E, I consume it, and I go to state Y. So then all I have to do is, when I'm going to inherit those behaviors, I need to split my transition into an A-B transition and a C-D transition. Now, suppose it got further more complicated by the fact that you didn't specify an A, B, and then a C, D alone. You actually specified an A with a particular flag first, and then an A, B, and then a C, D. What would happen then? Well, then I need to be able to inherit the idea that, okay, sometimes the flag A goes here. I see. Yeah. So when I don't have a flag, it's easy, because I'll just inherit the exact, like, intersection of my inputs with the inputs that I potentially could match. Since I don't pin anything, I match anything no matter what flags it pins, as long as it has at least an non-zero intersection in the input space. Right. But if I do have a flag, it gets more complicated. Suppose I pin a flag down, then I'm saying, when I go to peek into this next state and pull its stuff into me, when I look into that state and try to inherit its behavior into myself so that I can use its consume, I don't necessarily apply everything just because it intersects with the inputs that I specified, right? Because if I pin a flag down, that means that if I look at your case handlers and you can handle my input, but you also happen to, when in your case handler for that input, pin the flag the opposite way, that actually doesn't apply to me then. I need to keep looking for a fallback or a different handler that has that input or something like that. So if I say on case A, on input A with flag 1 set, do not consume and transition to state 2 or whatever, transition to state B or whatever, I don't know. Transition to state 2. State 2 says on input A with flag 1 not set, do some blah blah blah. Fallback, do some blah blah blah, right? I need to be able to deduce that I need to inherit the la 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 actions into my handler for A. And I deduce that by saying, hey, I am this set of things. I looked at the first thing, the first handler, and when I intersected those two, it was empty because we had conflicting pins. When I intersected the second two things, I found that I had something I could use. So I inherited it, and the thing I inherited, may have redundant handling information, right? It might not have fully eclipsed itself. I get it now. I get it. So I actually can get away with this. I am going to have to write a more generic set system for all of this anyway, but what I'm doing here for the case generation is fine. Because even if I don't fully note down all the information, like, hey, this fallback actually doesn't handle this particular flag being set to 1 for these set of characters because this other thing already handled that, and so it pins 0 for those characters but doesn't pin 0 for any of the other characters that it handles. I don't need to note that, because if I go through this inheriting process, I'm going to find something I can inherit before I get to the fallback anyway. And I'm going to inherit the first thing that matches just as if I was executing it and looking for the match, right? So it's fine. It's fine. I do need to be able to have multiple flags pinned, but I don't need to be able to have some flags pinned for some inputs and not for others, at least not here. I might still end up needing that. We'll see. It's confusing because there's a possibility that it would just be much easier if I did the full set, because then this could just be written as set operations, right? Construct the set, construct a full set, pin the flag if necessary, and then do the eclipsing operations on all the previous things to find out what's left over, and then save that as the set. I think if we went that way, I could just get it all right, and it might be a little bit like heftier of a data structure at that point, but it would let me be confident that I was getting this right without having to think about it so much. So that's what I'm going to try. So here's how this is changing. this is a condition flag, that's fine. SMI that's fine. Transition condition kind, so that's fine. Right. Yeah, so flag pins. Yes. Okay. I see. I see. I see how I can do this. Okay. Now, in order to do SMI case properly, I just need to implement full-on set operations for all of these things. So let's see if that's possible. Transition condition set. Yeah, so we're going to return a new one. SMI condition set. We're going to try to make an intersect. And that's going to take an A and a B, and it's also going to take an arena so that it can allocate a new set and not modify A or B for the return. And I also want one that's set subtract. Right, so A minus B. I'm not sure we need union, but it wouldn't be that hard to do because it would actually be the easiest one, so I'm not that worried about it. You could do it the sloppy way, or you could subtract A from B and then just append B to A, right? Now, this is currently being set up as a singly linked list for which there is no head and tail pointer, which might be a mistake. I might actually want condition set to be like this, and then have like condition nodes, right? And call this the node, right? And then this here is actually not pointers. Okay, I think that that's going to work. So let's see if we can implement condition set intersect and condition set subtract. This might become a two-parter because of how much it worked out. Like I said, this is the more sophisticated part. I warned you last time that this is not going to be the easy part, just because this notion of looking ahead and making sure we're basically trying to say that, hey, if I told you specifically which input and which bit field to deal with, you could easily solve this problem. You would say, here's the input I'm looking for. I look at the destination state and say, what's your handler look like for this? Does it peak or does it consume the input? And if it consumes the input, we grab it all and we're done. If it peaks, we grab it all, but then we do this again and look at its, and we just keep going like that, right? It would not be that complicated. The hard part is that we don't want to, for every combination of bits and for every possible input, which is something like 131,000 combinations, we don't want to represent all of those combinations as individual, like declared things that we pass through as separate handlers, right? We want our handlers to be chunkier than that so that we don't need so many of them. It's just easier to declare them that way, and it's easier to iterate them and optimize stuff, simplify things, etc. But then when it comes time to do this kind of work, the information we have is not very granular, and it has to do this fairly abstract, like this set of things, how does it apply, like when it reaches forward, it's like, oh, that set of things divides in this set of way, like these sets are the subsets of that thing that make up the continuation, and oh, of those, these three need to keep going, and it just becomes this much more abstractly, like, we're trying to avoid you know, dropping down to the really one at a time way of handling it, but we're still trying to make it work as if we were dropping down to that. So it just becomes this like trying to like represent things as sets so that you have like this entire set that you can operate on, but then you don't want that set to actually be the full list of everything, because that's what exactly you're trying to avoid, is handling each and every one of them. You need to represent your sets in some kind of more compressed way is the idea here. So given these two representations of a condition set, what does it look like to intersect them? Well, basically what we're going to do is say for each condition node in A, intersect that node with all of the nodes in B. If anything is left over, that node still exists, and put it into an output thing, right? So I think the way to do this is going to be like this. We're going to have a result, and then we're going to do a loop over A, and every time we visit a new node, we're going to immediately allocate a new node onto this arena. Whoops. Right? And the only thing is we're not necessarily going to push it onto the arena or onto the result right away. What we are going to do is we're going to say that the new node is an exact copy of the node we're looking at, and then we're going to do the node-wise eclipsing. So what we want to do is look at all the Bs. Oops. And I'll name these like B node or something like that. Transition condition node B node equals B dot first. So we want to look at each of the B nodes, and what we want to ask ourselves is, can we determine if there are any part of the space that this node represents that is also present in B? I'm doing this the wrong way, aren't I? This is how subtraction needs to work. I was thinking subtract, but I was implementing it in the wrong spot. So we want to look at everything in B and say, is there anything that is left over in node when we take out all the things that are in B node? Essentially, the way this works, since I didn't explain it by the way, is this is a set. Each of these nodes sort of describes a set, but they can't possibly describe all possible sets in the space, and so what we do is we chain them together. So if we need to end up doing something like, for these inputs it's these flags, and for those inputs it's those flags, it's two different nodes, and every time we need to bisect the set by like, okay, there are different, like, there's a portion, like this corner is gone, but these three corners are here, well, it's like split it in the middle, there's one node, there's one node. Oh, and then it turns out that like you gotta like carve out like this chunk here in this particular way. Oh, so that like rectangle is gone, but that right, I don't know if that is a way to describe it that actually helps anyone understand, but that's the way I'm looking at it. So what we want to do is say, okay, when we're looking at this node here, we're trying to subtract it out from us. So this is using the eclipsing rules. If the node I'm looking at does not pin any flags, then its inputs, then that set includes basically all possible bit patterns, right? So what we first want to do is we want to, like in the eclipter, we want to say either this node applies, either the flags in this node rule it out from overlapping with me. Its flags never overlap with me because we have somewhere pinned contradictory flags, or that we don't, in which case its inputs do eclipse my inputs. But it only eclipses my inputs for those places where its pinned flags are applied, right? So it's a little bit more complicated, but we want something like this logic here first. So what I want to do is I want to say overlapping flag checks. Actually, that logic isn't quite right anymore. Yeah. So I guess the way I actually want to do this is first I want to intersect the two inputs for the both nodes. And if that's empty, then it can't subtract anything from this node. If it is non-empty, then it needs to split this node into two nodes. I see. Obviously, yeah. That should do it. This should do it. So I need SMI condition set subtract. That updates my partial. Well, maybe I don't even want to pull that out into a separate function, I don't know. But I definitely need to do it like this. So then what I'm doing is I'm saying, okay, for each B node, we want to create a new partial. I don't know, it'll just be easier to pull this out into a separate function, I think. I'll be able to think it through more clearly. SMI partial condition set subtract. So the way this is going to work, I'm going to give it another arena. I'm going to give it partial, so I want it to update to take partial as the set and subtract out just the B node. Wait, there's an easier way to do this. I see it now. I'm iterating things in the wrong order. Okay, let's actually try it this way. Suppose I iterate the B nodes first. And the reason for doing that is what we have to do is every time we go through this process, we're going to... Okay, I see. So actually, I was on the right track with this, but it doesn't nest. It's actually two separate loops. This is weird. So I need to copy result.first, result.last, new node, result.count. So I need to copy set A into result completely. So do a full copy of the nodes first. And by the way, that doesn't even actually work because this is copying the input pointer, but there's a good chance I might want to modify that, right? No. I see. I just need to do result equals A. We're never going to modify it in place, so that's fine. Okay, got it. So for each B node, what I want to do is take a look at the A node, and I want to see how does this B node dissect or split up the nodes that I'm looking at, right? So what I'm not describing this in a particularly great way, but basically the concept is going to be, let's do a for loop. At each stage of the for loop, I am going to take an A node by going result.first. I'm going to call them P1 and P2, actually. We'll figure out what to do with result eventually. But we're going to take P1.first. And we're going to set P2 right here to be null, not out there. And the goal is now, we want to say, does this node node. SMI split node, split condition node, split node by this node, and that's going to give me a pair of new nodes or a single node, so I need something like better yet, we'll just do it this way. So okay. Alright, so that is, it's either going to be 1 or 2. If it's 1, then nothing happened. The new node isn't 2 separate nodes. It might still be less than this node, right? But there's not going to be more than 2, I don't think, nodes. So we figure out how many nodes there are. Then what we do is we say, okay, we need to take I guess I want to do it more like this. Second node equals new node next. And then I'm going to say SLQ push P2 first, P2 last, new node, P2.count plus equals 1. Then do all that again except on second node if second node actually exists. Make sense? Da, 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 da.